In the previous video, we got notes on organochlorine compounds. As we discussed, bioaccumulation, biomagnification, and persistence in environment are the major drawbacks of organochlorine compounds. Unlike organochlorine compounds, organophosphorus compounds do not bioaccumulate or persistent in environment, which explain that these compounds do readily break down in the environment in the presence of sunlight, microorganisms or other forces. Yes, today we are discussing organophosphorus compounds. As the name suggests, these compounds contains phosphorus as a key element in their structure. Being water soluble structures, organophosphorus compounds shows systemic properties in the plant system. The systemic properties of any pesticide or insecticide are of mainly three types. The first one is xylem mobile pesticides, amphimobile pesticides, and translaminar pesticides. In the other words, the movement of the pesticides can also be coined as acropetal movement, basipetal movement. So in the xylem mobile or acropetal movement of the pesticide, the movement of the pesticide molecule happens with the aid of xylem tissues, and this movement is often upward in the plant tissue. So the movement of the pesticide molecule happens with the aid of xylem tissues. So the movement is often upward in the plant system. So in the amphimobile or basipetal movement, the movement or translocation of any pesticide molecule happens with the aid of both the xylem and phloem tissues, and the movement is often both upward and downward in the plant system. So the third one is translaminar pesticides. So the translaminar pesticides, the pesticides which are applied on the upper surface of the leaf will readily translocate to the untreated lower surface of the leaf, and supplies enough dosage of that particular pesticide to cause lethal effects on the insects which are feeding on the upper surface of the leaf. So this is about the systemic properties of pesticides. So our OP compounds are majorly xylem mobile pesticides, xylem mobile insecticides, or translaminar insecticides. And now we are discussing two major reactions which are helpful to synthesize organophosphorus compounds. The first one is Arbuzov reaction. So in Arbuzov reaction, the Arbuzov reaction is the most important reaction to form phosphorus and carbon bonds. So in Arbuzov reaction, what trialkyl phosphates reacts with alkyl halide to give pentavalent phosphonates. So this is Arbuzov reaction. So in the Arbuzov reaction, trialkyl phosphate reacts with alkyl halide to give phosphonate. So the major change here we have to observe is the trivalent of the phosphorus has changed to pentavalent, and this reaction is useful to synthesize phosphonate, phosphoric acid esters, and phosphite oxides. So in this reaction, primary alkyl halides reacts normally with the trialkyl phosphates, but tertiary alkyl halides and simple aryl and vinyl halides do not react with the trialkyl phosphates. So in order to get the end product, we have to choose always the primary alkyl halides. So this is about Arbuzov reaction. And the next reaction is Parco reaction. So this is Parco reaction. So in the Parco reaction, trialkyl phosphate reacts with alpha halogenated carbonyl compound to yield vinyl phosphate. So this is the Perko reaction. So this Perko reaction is useful to synthesize vinyl phosphates like monochromatophos, dichlorophos, or we often call DDVP, and phosphomidone. So in the Perko reaction, the phosphorus may attack either on the halogen or alpha carbon or carbonyl carbon or carbonyl oxygen. So the attack may be, the probability of attack may be at the four sides, but the end product will be always vinyl phosphate. So this is the Perko reaction. So these two reactions, the Perko reaction and the observed reaction are very important in the synthesis of organophosphorus compounds. Organophosphorus compounds are broad spectrum insecticides causing lethal effects to the wide range of insects even at very low concentrations. These organophosphorus compounds are strong nerve poisons having low LD50 values. So having low LD50 values make opaque organophosphorus compounds very dangerous to use in agriculture. In spite of the danger associated with organophosphorus compounds, these insecticides have a significant importance in the pesticide market. And now let's look into how organophosphorus compounds cause mortality in the insects. As I mentioned earlier, organophosphorus compounds are strong nerve poisons, which means they do directly act on the nervous system of the insect. So we are very much familiar that the nervous system consists of neurons. These neurons are useful to pass the message in the form of impulse from one place to the other place. So in the nervous system, in between two neurons, there is a space called synaptic cleft. So at the synaptic cleft we have a neurotransmitter. So at the synaptic cleft we have neurotransmitter. So the role of this neurotransmitter is to allow the impulse pass from one neuron to the other neuron, so via that synaptic cleft. So in the central nervous system, acetylcholine act as a neurotransmitter. Acetylcholine. So in the central nervous system, acetylcholine act as neurotransmitter. So immediately after each impulse, this acetylcholine with the aid of an enzyme called acetylcholine esterase. In the presence of acetylcholine esterase, these acetylcholine hydrolyzes into choline and acetic acid. So with the presence of acetylcholine esterase, acetylcholine hydrolyzes into choline and acetic acid. Our organophosphorus compounds block the acetylcholine esterase enzyme and causes lethal effect. So on the acetylcholine esterase enzyme we have two sites. The first one is anionic site and the esteric site. The negatively charged anionic site attracts towards the positively charged quaternary nitrogen, and there will be a bond formation between these two sites. And the next one, so the second site is esteric site. So on the esteric site we have two important amino acids, that is serine and histidine. In the serine we have hydroxyl group. So a bond forms between the hydrogen atom of hydroxyl group of serine and carbon atom of carboxyl group of acetylcholine. So this bond will form. So a bond forms between oxygen atom of hydroxyl group of serine and carbon atom of carboxyl group of acetylcholine. So after formation of this bond, the bond breaks at the oxygen. So after forming these two bonds, the bond will break at the oxygen and form choline and acetic acid. So choline and acetic acid will be formed with the help of hydrogen atoms which are supplied by acetylcholine esterase enzyme. So this is how normal reaction takes, this is the normal reaction takes place at the synaptic cleft. So our organophosphorus compounds binds to this hydroxyl group. So they gonna bind with OP compounds, and there won't be, so after binding the OP compounds to this hydroxyl group, there won't be breakdown of acetylcholine into choline and acetic acid. So the normal process will be blocked. So this leads to the accumulation of acetylcholine at the synaptic cleft. So this is how organophosphorus compounds act on the nervous